Signals and Systems, CT Fourier Transforms II Properties, Series on Signals and Systems, lecture number 3.12. Continuous time Fourier transforms. They are useful in converting continuous time non-periodic signals from time domain to frequency domain and vice versa. These transforms exhibit several interesting and useful properties: linearity property, duality property, shifting property, scaling property, differentiation property, integration property, convolution property. These are some of the properties of CT Fourier transforms, which we are going to consider in the present session for their understanding at a deeper level. With this small introduction to the session, now we move further and start the session by reminding the defining relations of CT Fourier transform. The Fourier transform f of omega, it is called spectral density function. For a CT non-periodic signal, f of t is defined as f of omega is integral minus infinity to plus infinity f of t e power minus j omega t dt. This is a forward transform. It transforms time domain signal into frequency domain signal. This equation is called analysis equation. Inverse transform is also there. It is called reverse transform. It converts signal in frequency domain into signal into time domain. F of t is equal to 1 by 2 pi integral minus infinity to plus infinity f of omega e power j omega t d omega. The frequency domain signal f of omega is in general a complex function of angular frequency omega. As already mentioned, it is called spectral density function. In the discussion, in the description, which we are going to do right now, uses these two defining relations quite frequently. That for this reason, they are being mentioned, repeated here again. Now we consider linearity property and duality property of CT Fourier transforms. Linearity. CT Fourier transform obeys linearity property. Mathematically, it can be stated as Fourier transform of A f1 of t plus b f2 of t is A f1 of omega plus b f2 of omega. Here f1 omega is Fourier transform of f1t, f2 of omega is Fourier transform of f2 of t. In word form, linearity property can be stated that the Fourier transform of a weighted sum of two signals, AF1, BF2 plus, it is weighted sum of two signals, is equal to same weighted sum of, here in place of the, same is more appropriate term, same weighted sum of individual Fourier transform. Proof is so simple, it's trivial. Another property, duality. Fourier transform of f of t is 2 pi f of minus omega. Notice here it is capital F. It pertains to spectral density function. Right side we have small f. It pertains to time domain function. Now, how this property has come? What is the validity of this property? We see 2 pi f of minus t is integral minus infinity to plus infinity f of omega e power minus j omega t d omega. This expression is from reverse transform. Replace omega by x. It results in 2 pi f of minus t becomes equal to integral minus infinity to plus infinity f of x e power minus j xt dx. Hence, 2 pi f of minus omega is equal to minus infinity to plus infinity fx e power minus jx omega dx. Now replacing variable x by another variable t, we get 2 pi f of minus omega equal to minus infinity to plus infinity f of t e power minus j t omega dt. Of course, it can be noticed it is Fourier transform of capital F of t. Therefore, f of t and 2 pi f of minus omega, these two are transform pair. The symmetry holds perfectly if f of t is an even function. In that case, f of t, 2 pi f of omega, they become pair, transform pair. Another property we consider, it is called conjugation property. It is more relevant to complex valued signals. It is usually referred to as conjugation symmetry. F of t conjugate, star indicates conjugate. Its Fourier transform is conjugate of f of minus omega. Notice in all these descriptions, explanations, f of t, capital F of omega. These are transform pair. Now, some information regarding conjugation symmetry. Conjugation or Hermitian symmetry. The complex function f of omega is said to be exhibiting Hermitian symmetry if f of minus omega is equal to conjugate of f of omega. So if the magnitude function exhibits even symmetry and phase function exhibits odd symmetry, then the complex function is said to be exhibiting Hermitian symmetry. So Hermitian symmetry implies magnitude functions even symmetry and phase functions odd symmetry. If the signal f of t is real, then its spectrum f of omega possesses Hermitian symmetry. It can be proved without much difficulty. Fourier transform of conjugate of f of t is minus infinity to plus infinity over integral sign conjugate of f of t e power minus j omega t dt. This is defining a relation of transform. Then it can be manipulated slightly, resulting in it being equal to conjugate of f of minus omega. We move on to another property, scaling property. Scaling property in mathematical form states that Fourier transform of f of a is a constant. It is 1 by mod a f of omega by a. How this relation has come? How can one say that scaling property is exhibited by CT Fourier transform? A small proof is given here. For a positive real constant a, Fourier transform of f of at is integral minus infinity to plus infinity f of at e power minus j omega t dt. This is defining relation. Let x equal to at. Then Fourier transform of f of a t, it becomes 1 by a minus infinity to plus infinity over integral sign f of x e power minus j omega by a x dx. Of course, this can be identified as 1 by a f of omega by a. Similarly, even when a is less than 0, it can be shown Fourier transform obeys scaling property. When a is less than 0, what happens? Fourier transform of f of a t becomes minus 1 by a f of omega by a. Combining these two, one for a positive, another for a negative. Combining these two, we have this scaling property relation. Another property is shifting, time shifting. This property can be stated as Fourier transform of f of t minus t naught is f of omega e power minus j omega t naught. From the defining relation, Fourier transform of f of t minus t naught is integral minus infinity to plus infinity f of t minus t naught e power minus j omega t dt. Let t minus t naught is equal to x. Then Fourier transform of f of t minus t naught becomes integral minus infinity to plus infinity f of x e power minus j omega x plus t naught t. It can be identified as Fourier transform f of omega e power minus j omega t naught. Hence, shifting property, time shifting property. Fourier transform of f of t minus t naught is Fourier transform of f of t multiplied by e power minus j omega t naught. Now we consider another shifting property, that is frequency shifting property. Mathematically, this property can be stated as Fourier transform of f of t e power j omega naught t is capital F of omega minus omega naught. Notice earlier shifting is in time domain. Now here it is in frequency domain. Proof can be easily understood from the defining relation. Fourier transform of f of t e power j omega naught t. Defining relation says it is integral minus infinity to plus infinity f of t e power minus j omega naught t multiplied by e power minus j omega t dt. This can be manipulated, simple manipulation. And after manipulation, it can be found equal to f of omega minus omega naught. So this is a proof to say that frequency shifting property of CT Fourier transforms. Now we consider time differentiation. Fourier transform of n times differentiation of f of t is j omega power n f of omega. The proof of this particular statement one can have by considering reverse Fourier transform. F of t is 1 by 2 pi integral minus infinity to plus infinity f of omega e power j omega t d omega. This is reverse transform. Now differentiate both sides. df by dt is equal to 1 by 2 pi d by dt integral minus infinity to plus infinity f of omega e power j omega t d omega. Changing the order of differentiation and integration, we get df by dt is 1 by 2 pi minus infinity to plus infinity j omega f of omega e power j omega t d omega. Now it is so clear, one can easily see Fourier transform of df by dt is j omega f of omega. This result can be extended to nth derivative 2. Therefore, Fourier transform of nth derivative of f of t is j omega power n f of omega. Now we consider differentiation, but now it is in frequency domain, frequency differentiation. This property in mathematical form states that Fourier transform of minus jt power n multiplied by f of t is nth derivative of f of omega. Here differentiation is with respect to omega. So now how this property is obeyed by Fourier transform. Consider forward relation. F of omega is integral f of t e power minus j omega t dt. Differentiate this relation both sides. It results in df by d omega, which is equal to d by d omega integral f of t e power minus j omega t dt. Changing the order of differentiation and integration, we get df by d omega is integral minus infinity to plus infinity minus jt f of t e power minus j omega t dt. Now it can be easily understood that minus jt f of t, the Fourier transform of this product is df by d omega. The result can be extended to nth derivative. It results in Fourier transform of the product minus jt power n f of t is nth derivative of f of omega. Now we consider integration. First, time integration or integration in time domain. This property in mathematical form states that integral minus infinity to t f of tau d tau. The Fourier transform of this particular integral is 1 of j omega f of omega plus pi delta of omega f of 0. Two terms are there. Now, to have a proof of this statement, we consider convolution. One can identify that minus infinity to t power integral sign f of tau d tau. It is convolution between f of t and unit step function. Using the fact that time domain convolution is equivalent to frequency domain multiplication, now we apply transform on both sides. It results in Fourier transform of integration minus infinity to t f of tau d tau. It becomes equal to f of omega 1 by j omega plus pi delta omega. Therefore, Fourier transform of integration from minus infinity to t f of tau d tau. It becomes equal to 1 by j omega f of omega plus pi delta omega f of 0. In this description or derivation, we used the fact that transform of unit step is u of t is 1 by j omega plus pi delta of omega. Delta means impulse function. So notice in the explanation that is given here, we used two facts. One is convolution of f of t with u of t is integral minus infinity to t f of tau d tau. Another is Fourier transform of unit step is 1 by j omega plus pi delta of omega. These two aspects we discuss again in the coming session or sessions. Frequency integration. According to this property, frequency integration, Fourier transform of 1 by minus jt multiplied by f of t. This product, its Fourier transform is integration over f of omega d omega. To have a proof, to have a deeper level understanding of this property, consider Fourier transform of integral f of omega d omega. It becomes double integration with the proper limits, appropriate limits, over f of t e power minus j omega t dt d omega. This can be manipulated, integrated, and limits can be substituted and found that it is Fourier transform of f of t by jt. Convolution. First we consider time convolution and then we consider frequency convolution. Time convolution means convolution between two time domain signals. Frequency convolution means convolution between two frequency domain signals. Now time convolution. Fourier transform of convolution between two signals f1 of t, f2 of t. It is f1 of omega multiplied by f2 of omega. Notice in time domain it is convolution, in frequency domain it is multiplication. The convolution in time domain is appearing as multiplication in frequency domain. We are going to see convolution in frequency domain. It appears as multiplication in time domain. To have a proof for this statement, time convolution, consider Fourier transform of two convolving functions f1 of t, f2 of t. It is equal to integral sign minus infinity to plus infinity e power minus j omega t, integration minus infinity to plus infinity f1 of tau, f2 of t minus tau d tau. Notice whatever is there in the square brackets, it is the definition of convolution. Remaining is Fourier transform definition, forward transform definition. Now this integration, two integrations are there. This can be manipulated and can be found as product of two functions f1 of omega, f2 of omega. f1 of omega is Fourier transform of f1 of t, f2 of omega is Fourier transform of f2 of t. Then we move on to frequency convolution. Here convolution is happening in frequency domain. This property states that Fourier transform of f1 of t multiplied by f2 of t is 1 by 2 pi f1 of omega convolution with f2 of omega. Notice here convolution is in frequency domain and multiplication is in time domain. The convolution in one domain, it leads to multiplication in the other domain. Now we come to the end of this session. To recollect, we considered various properties of Fourier transforms like linearity property, duality property, shifting property, integration property, convolution property, etc. Hope this session is useful to you. We meet again in another session with a new topic soon.